Alright, so this is a video to review for the Unit 5 test. I'm going to go through much of the same things that I would be doing in class, so you're not missing out on anything. But of course, if this video is not enough, just send me an email, let me know, and I'll be happy to provide whatever else you need. First thing we'll do is just start with one more Riemann sum. So at any point during the video, you may want to pause and just try the problem yourself before I go through it, just to make sure you understand. But on the test, I'm just going to ask you to set up and show me that you can calculate a basic left-hand, right-hand sum. It's a skill you'll need for AP Calculus and just moving forward with other things. So we need to make sure you can still do it, even though we do know how to find these answers exactly now. And again, we're thinking of just adding up rectangles. This function looks like this. So our left-hand sum will be an overestimate and our right-hand sum will be an underestimate if we cared about that. But we don't even need the rectangles, right? We can just think about getting our x values. We're going to chop this into 4 subintervals. So we'll say 2 minus 1 over 4, which equals 1/4. Okay, so each of our subintervals is going to be 1/4 of a unit long. And then, our heights of our rectangles, some students like to make a number line. And then 1.25, 1.5, 1.75. Do this however, it works for you, but the key thing is you need the setup. So, okay, left-hand sum, right-hand sum, and then we always know the width is going to be 1/4. And then it's a matter of plugging in our values. Oops, yeah, no, that's right. Right, if there's 4 subintervals, then you should have 4 function values that you're adding up. Those correspond to the heights of the rectangles that we'd be using. Right, and likewise, setting up our right-hand sum. Okay, we would start with the right-hand endpoint and work our way over, but it ends up being these. When you're taking the UConn test or AP test or whatever, they're going to want to see this initial setup. Okay, so write it, please, just like I'm writing it is safe. But how you get there is up to you. If you don't need any of the scratch work to get there, that's fine. If you can just jump right to setting it up, that is totally okay. The thing you would then need to do is calculate this. So I'm going to go ahead and do that. You may just want to jump ahead in the video for a moment. But I will go ahead and find this, so just be patient. Probably should have done this before recording. Oh well. It'll just take me a minute. Okay, you're responsible for knowing how to use the technology to do this. That said, Desmos will do this pretty easily for you. So you could always just use that. I'm just going to round to 3 places, so it ends up being 3-1. You can do the same thing on the test, and then remember, you just go back and just change the 1 to a 2, and that'll work. All right, I get 6.28125, so we'll just say 1. That's fine. All right, so it ends up that the left-hand sum overestimates, and again, you can think about the picture and why that's the case, right? If you graph this function coming from the left, the rectangles are bigger. Coming from the right, the rectangles would be smaller. Now you can actually sort of check this, before you didn't know how to do this, but we know we could find the actual answer by taking an integral from 1 to 2 of 9 minus x squared. And you could use fundamental theorem. I'm just going to go ahead and use my calculator real quick to do that. Let me get a good viewing window. Oops, 0.6. Remember, second trace integral will do it. Or Desmos can do this just fine. So the actual answer that my calculator is giving me is 6.6 repeating, or 6 2/3. Okay, which is certainly in between those two results, so we can feel pretty good, and the results we got are close to that number. Okay, so we can feel like we probably did the left-hand sum correctly and the right-hand sum. It's super easy to make a calculator mistake. Okay, if you set it up correctly, but you get the wrong answer, I'm just going to take a point off. Okay, it's not the end of the world, but just you might want to take some time to double check. All right. You don't have to find the actual answer. That's just a way to check. You do need to know all the antiderivative rules, of course. So you may want to pause the video at this point. Try to do these as quickly as you possibly can. All right, and then I will go through and find them all. Okay, so this one is, now you need a plus C on all of them. If you forgot your plus C, well, you should feel a little bad. I was going to say don't feel bad. You should feel a little bad, because you would lose a point every single time. Okay, so these first few are just basic power rule. Okay, with the 3 in front, we just leave it there. 2 just becomes 2x. Think about the derivative of 2x would be 2. So you're just undoing that. Sine becomes negative cosine, careful. Cosine becomes positive sine. Again, just think of your derivative rules backwards. Secant tangent would normally be secant, so negative secant tangent would just be negative secant. E to the x is just e to the x. This would be 5x to the 8th over 8. Okay. Square root, remember it's easiest just to think of this x to the 1/2. So we would say x to the 3/2 over 3/2. I'd really like you to take the reciprocal though, just that looks better. Okay, cube root, again, think of that as x to the 1/3. And so the final answer is going to be 3/4 x to the 4/3 when you clean everything up. This one here, it is easiest to think of this as just being 3/4 x to the -5th, right? Bring it up. And so this one, let's do it out. So 3/4 x to the -4 over -4. All right, so now let's bring everything back down and clean that up. Okay, so you add 1 to the exponent, divide by the new exponent. And so that's going to be -3 over, right, 4 times 4 is 16x to the 4th plus c. It's okay if you wait until the final answer to throw your plus c in there. You don't need it for the scratch work. That's fine. 5 over the square root of x. So again, make this 5x to the -1/2. So that's going to be 5x to the +1/2 over +1/2. Okay, so taking the reciprocal is going to give us 10. 10. You can say x to the 1/2 is fine if you want to just leave it like that. If you want to make it the square root of x, that's fine. And then obviously plus c. From now on, the exponent or the square root doesn't matter. All right, and then just be careful. A lot of students will try to do power rule here, but then you try to do that and you get 0 over 0, which you can't do. Okay, so you just need to remember that that is a special rule. Okay, ln of x. And you do need the absolute value bars there. But if you forgot them, for now I'm just going to make the correction. Okay, in AP Calculus, you'll care a little bit more about that. This is not obviously every single rule, but this is a good, look at all of them anyway. And, you need to know trig rules, and I would make a list, write them down somewhere. The test is open notes anyway, so may as well just have all that stuff. All right. You need to know how to use antiderivatives in a context. So we've seen that the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. And so, to connect this to things that you're going to be doing, a lot of times you'll see a question like this. So you're given an acceleration function, they want you to find a position function. And so the first thing we do is we begin by integrating with respect to time. Okay, both sides of our equation. The integral of acceleration is simply velocity. You don't need to think about that. And then that's going to be 2t squared. But then we need a plus c. We fill in our information now. Right? They are giving us some initial condition. So we go ahead and plug that in. And we solve for our c. So that's going to be 18. Taking away is going to give us -14. So now we have a velocity function. And from there, we can integrate one more time with respect to time, and we get position. Okay, so this will be 2t cubed over 3 minus 14t plus, now we would say c, but really, it's a different c, so we should probably label these. call the first one C1 and call the next one C2, just so you don't get them confused and you don't plug the wrong C in the wrong place. And then it's just a matter of plugging in again. So you're really doing the same thing twice. And I'm going to have to get my calculator for this, but you would go ahead and solve for C2 at this point. So let me just do that real quick. 2/3 times 125 minus 14 times 5. All right, so I get 13.3333. So 6 minus that answer is going to give me negative 7.3 repeating. You can leave decimals on the UConn test. This is considered exact, right? As long as you put the repeating decimal there, that's okay. Of course, you can make that into a fraction if you chose. It would be negative 22/3 would also be fine. Okay, and then the final answer, right? They want a function, so you should go ahead and plug all your things in. Minus 14t minus 22/3. And you're done. They might ask you to do something with the position function. They may say like find the position at time 10, and then you would just plug it in or something. But that is what's considered an initial value problem. All right. You should know how to work with definite integrals. Just finding a definite integral. So, if I asked you to do the fundamental theorem for 1 to 2 of, like we did 9 minus x squared before. Okay, you should know what that means. You should know that you take your antiderivative and you plug in your bounds and you subtract. Plug in 1, you get that. Okay, and whatever that comes out to would be your answer. So you should just know if I give you straight up a definite integral, here's how you do it. Take antiderivative, plug in bounds. Okay, that's the fundamental theorem of calculus. But we should also be able to interpret the definite integral, with geometry and thinking about what it represents as area underneath a curve. And so that is what I've drawn over here. Is we have some function f of x. And let's just assume these are geometric shapes. So you can assume that's a semicircle, and you can assume those are straight lines. And let's say this is called little f. So let's say I wanted to integrate from 0 to 2 of little f. Okay, well, you could go ahead and find an equation. From geometry, you know the equations of circles and things. But we don't need to do that because we just need to know that this represents the area from 0 to 2. Okay, so that is one way to interpret the definite integral is to think of it as I'm finding this red shaded region. Well, that's just a quarter of a circle, so why don't we just do that, right? Let's just do 1/4 pi r squared. So the radius of this circle is 2, right? Okay, and so this works out really nicely. 4 is going to cancel with 1/4, and so we get pi. Of course, we need to be careful, right? This is area below the x-axis. So remember, we say that's going to be negative accumulation. And so the answer to this integral is, although the geometric area comes out to pi, the actual answer to this is going to be negative pi. Okay, so area below the x-axis comes out negative. The reason you want to think of it that way is that way it allows the particle to move backwards, right? When the velocity, if f represented velocity, this would mean the particle is moving backwards. Remember, we said area under a velocity curve gives displacement. So this would represent like the particle is going to move backwards by negative pi units. Okay, that's why we allow for a negative area, even though we said in geometry, right, you don't want area to be negative. This is a different context. All right, if you were going to integrate from 0 to 6, okay, you don't have to do all the work again. You already know this, so now you just need to calculate this part here. So you think of it as you're going to integrate all the area from here to here. And so, okay, you have a triangle from a height of 2 and a base of 4, so it's going to be negative pi, right, to take care of the 0 to 2 part. But then we're going to add the area of this triangle. So what is it? 1/2 base is 4, height is 2, so it comes out to just 4. And you would just leave it, right? You can't combine that any further, so you just leave it as negative pi plus 4 or 4 minus pi. If I asked you to integrate backwards, okay, remember that you get the opposite thing. So if I said 2 to 0, it's going to be the same exact answer as 0 to 2, just the opposite. So you're going to get pi. And remember, that comes from when you do the fundamental theorem, you would be switching your bounds. So you would be doing exactly the same subtraction, just the opposite way, so you end up getting the opposite answer. And then, of course, if I integrate from anything to itself, maybe pick a number different than 0. If I integrate from 2 to 2, well, it's like I didn't really do anything at all, and so I just get 0. Okay, so you should understand how to integrate both with an equation and also just with a picture, understanding that it gives you accumulation under the curve. Okay, you should also understand how to interpret a definite integral in a context. Okay, so we give you this example: a population grows over time. The rate of change of that population is given by P of t. Okay, where it's in thousands of people over years. By how much will the population grow from time equals 1 to time equals 5? Okay, notice at no point do we know what the population is. They're not telling us what the population is currently. We don't know what it's going to be, but we don't need to know that. We just need to know how much it is growing by. And so the key thing that you need to know, and you may want to write this down somewhere, right, is that the integral of a rate of change is going to give you an amount of change from time equals a to time equals b. Okay, so it will tell you the difference between the final amount minus the starting amount. And so in this case, it will tell us the difference between the final population and the starting population. And so sometimes we say this is the net amount of change. Okay, so you would just simply integrate from 1 to 5 to t plus 3 dt. That simple. Okay, just setting up that integral. But you need to understand that that integral is going to find the answer to this question. And so that gives you t squared plus 3t. Okay, plug in your bounds, and so you're going to get 25 plus 15 minus 1 plus 3, and so that's 40 minus 4, which is 36. Okay, well, in context, right, what does that mean? That means the population went up by 36,000 people. We don't know where it started. We don't know where it ends. Okay, but we have some population function. Well, we found the population function, right? This is it. And we know it's growing. Now, we don't know exactly where it began, and we don't know where it ended, but we know the difference is going to be 36,000. Okay, so make sure you understand that that connection, that context of the definite integral. We didn't do a lot with that in class. I have mentioned it a few times, but we didn't do a ton of examples. So. Right, and then of course you need to know how to do U substitution. So you may want to just take a minute, again, pause the video and see if you can do this one yourself. All right, so you would take U, x squared minus 1, du will be 2x dx. Okay, but then you want to get it to match, so we're going to multiply both sides by 4. And then we want to change our bounds. So you don't have to do this. You could wait until the very end and plug in your x's and then just use 2 and 1. But I think it's just easier to get your bounds at the beginning. So, okay, especially since in this case they work out fairly nice. You end up getting 3 and 0. Okay, so you're changing your x bounds into u bounds by plugging them into the u formula. Okay, now you're going to set up your integral. I'm going to pull out the 4. I'm going to use my new bounds. And then it is simply the square root of u du, which again, think of that as u to the 1/2. Leave the 4 in front. U to the 3/2 over 3/2. Okay, which is going to be 8 thirds u to the 3/2, and then you're going to plug in your bounds. You don't need a plus c here because you're doing a definite integral. Okay, plug them in. Of course, 0 is just going to go away. And 3 to the 3/2 power, without a calculator, that's not so nice. And if you were doing the UConn test, this is how you would leave it. Okay, this obviously just goes away, so you're done. Okay, you don't want to get a decimal, especially if it's going to be rounded off. That's all. A lot of U sub problems are just going to look like that. So if you can do this one, you're probably in pretty good shape. But remember, you have that tons of U sub practice that you could always do a bunch more if you wanted to make sure. Okay. The other type of U substitution you would see is something like this. Again, you may want to pause the video and just try this right now. All right, so remember we always choose the thing inside. Well, not always, but usually that's a good choice. Okay, careful, 2 dx for the du, and then we want to isolate x in terms of u. Okay, this allows us to set it up. We'll get 1/2 du equals dx, by the way. Okay, so I'm just going to go ahead and plug everything in, and then we'll talk about how to clean it up from there. U to the 10th power, and then 1/2 du. So then again, right, pull out these fractions to make life easier. Pull out this 1/2, but then you could also pull out this 1/2 to get 1/4. And then the idea is from here, you've created a much simpler integral. You do need to distribute. Okay, you cannot take that integral yet. U to the 11th power plus 7u to the 10th. Okay, and now you are able to integrate using just basic power rule. And then the very last thing you should always do when you're doing an indefinite integral is you should plug your x back in, because you are finding the answer to the original thing. And you win. All right, one last thing. Let's do one more example of this. Again, you might want to pause and try this yourself. Okay, on the test, I would ask you to show all the work, including finding the bounds. To do that, we simply set the functions equal to one another. Easiest thing to do is get it over and treat it like a quadratic. And you do end up getting a nice quadratic, of course. Because you're doing it by hand, you're going to get nice things. And won't be too mean. And so what that tells you is the intersections. And so, you should draw a picture to help you. And this is going to be a quadratic starting at 4 and pointing down. This is going to be a linear function with a y-intercept of 2. Okay, and so what you found is that it intercepts at -2 and +1. I probably didn't draw that picture completely correctly, but you don't need the picture to be perfect. You simply need the picture to help you decide which one's on top and which one's on bottom. That's all you really care about. And so setting this up, remember we always do the top function minus the bottom function. And so we are going to say the top is the quadratic in this case. And then we're going to integrate from -2 to 1. All right, clean that up. Okay, so I'm going to say 2 minus x squared minus x. You don't have to put it in descending order. Like, it's fine if you leave it like this. You can rearrange it if it bothers you. And then, I do want you to show me the fundamental theorem from here. Okay, so it'd be 2x minus x cubed over 3 minus x squared over 2. But you can also just use a calculator, so that's what I'm going to do. Oops. What happened there? 4 minus x squared minus x minus 2. I'll just be lazy and type it like that. All right, and so I get -2 to 1. I'm getting 4.5. Yeah, we keep getting 9/2 for these examples. It's because I'm choosing nice, easy, linear and quadratic things that work out nicely. So a lot of times, basically what we've been doing is the same picture, just shifted around a bunch of times. So like, it's just, we end up getting the same area. That's all. Purely a coincidence. All right, so what I've tried to do is to give you a broad overview of the various things you're responsible for. That said, if that's not enough for you, shoot me an email anytime. Let me know what's up. Let me know what you need. Let me know what questions you have. Let me know what extra practice you would like, and I will be certainly happy to do that. Okay, just reach out to me. Otherwise, have a great day.